This could not be more talk about technology. There's like 3 women in the room. I hope we will manage to have a better ratio at future talks. But I'm very happy to have you guys here. So a few words on why we are all in this room. This is the first meetup of QED-it. I'm not going to talk about the company too much. It's the people that you're going to see here on stage are the technology side of QED-it. So there's going to be Daniel, who comes from the Weizmann Institute. He did homomorphic encryption, and we took him to the company right before he continued to be a full PhD. We stopped him there. He said, please come to join us in the industry. There's Kobe, who develops everything in the company, and we actually have a new person joining, Roman, who's not going to present. The chief scientist of this company is called Aviv Zohar, Dr. Aviv Zohar from the Hebrew University. He unfortunately couldn't be here this evening because of severe back pain, but I'm sure he's going to look at everything, and his spirit is all over the slides that you're going to see. So what is this evening about? We want to talk to you about blockchain, just a tiny bit, and zero-knowledge proofs. So just to give it a little perspective, you probably all heard about Bitcoin and how and you got interested in Bitcoin like us. We're all passionate about this technology. There was an evolution in the past couple of years. The banks and big institutions have looked at what can you learn from Bitcoin, from this success to move value around, and they try to imitate part of this success and move it to the banking world. But as you know, in Bitcoin, the addresses are pseudonymous. You don't know who stands behind an address. And when you move this, when you take the concept of Bitcoin to banks, everyone that is going to send money is going to be known. You know who is playing. They're not copying the pseudonymity of Bitcoin. They want to have their own little blockchain. So it's called, this entire industry is now called the blockchain industry. And they want to copy concepts from the Bitcoin world and Ethereum and have it in private blockchains. And there's a problem there. The problem is if you know all the participants, you know who is behind an identity, and you reach a consensus between everyone by sending the transactions in the clear to everyone else, that means that one bank will have all its data, all the transactions leaked to all the other banks. They're very interested in having this the same mechanism as in Bitcoin, which is have like a big ledger, but they're not interested in sharing their confidential data with all their competitors. So they got into this world. They started, every large bank has now a group of technologists working on the blockchain space, on adapting this technology to banks. And these efforts reached a wall. They cannot take this technology and actually deploy it and make it happen in the real world. So this is, there is a solution to that. How can you reach a consensus between everyone, but not by sending the transactions to everyone? The way we solve it is using this piece of technology that's called zero-knowledge proof. And this evening is about what is zero-knowledge proof, how does it work, and a little bit a demo to show you how to write those proofs. So we're proud that this technology was invented in Israel, sometimes in the early 90s. This is Shafi Goldwasser, who co-wrote one of the most important, or the initial paper on zero-knowledge proof. So what is zero-knowledge proof? Just in a word. It's a cryptographic protocol that lets you prove to a third party, let's say a computation on confidential data without revealing that confidential data. So I will say it again in a different angle. It's a form of self-auditing. I have confidential data on my systems, like each bank has their own confidential data on their system. And a bank will run a little audit, a little program on its confidential data, have the result, and this result will be shared with the other participants. Not the underlying secret data or the secret transactions, just the result of a computation on that data. The blockchain is no longer a blockchain of transactions, it's a blockchain of proofs. So this, what I'm describing here is, let's say, a second iteration on the architecture of blockchains for the banks. What most of you are probably familiar is how Bitcoin works, right? You heard about mining and about transactions moving Bitcoins around. So we're going to set aside this world of Bitcoin and coins going around, and we're going to talk about information, confidential information, and how can you prove to other parties processing about this information. So, as I said, this technology, zero-knowledge proof, was invented in Israel. And to give a concrete example, I'm going to show you something that happened in 2013 at the World Championship of Sudoku. So I need to put this. All right, so what this person is doing is live trying to solve a 9x9 Sudoku faster than the other participants. And maybe you are aware of this, but there's a huge divide. So you're familiar with Sudoku. You need to have the 1 through 9 on the rows, the columns, and the squares. And this is going to be the example of what is a zero-knowledge proof. So there are the purists in Sudoku that say a Sudoku is only a 9x9 Sudoku. And there are the people that say, no, we can have larger Sudokus. And there's a huge divide between them. There's hatred between those two parties. And in 2013, there was the big Sudoku incident. What happened? During the marathon session of Sudokus, so this is so actually the real example is a much larger Sudoku. So during the marathon session of Sudoku, some purists from the 9-on-9 put a mistake in that Sudoku, and the participants sat in front of something that has no solution. And unfortunately, instead of trying to solve it in approximately 4 to 5 hours, they took 36, 48 hours without eating, just solving this Sudoku. Of course, I'm inventing all of this, right? One of them felt so ashamed that he immediately stopped Sudoku. So the problem there was, how can those participants know that there is a solution to that Sudoku problem without seeing the solution? Again, can I prove to someone? So the International Sudoku League decided that there is going to be now, before each marathon, each participant is going to get a proof of the existence of a solution to that Sudoku problem, but without revealing the solution. So can this be done? This is the basis of a zero-knowledge proof. A proof about a very difficult problem without seeing the solution itself. So I'm going to invite now Daniel to give us an example or an explanation on how can you solve this problem with this example of a hard Sudoku. And then we're going to dive a little bit deeper into the cryptography of how zero-knowledge proof works. So we are all the part about the connection to blockchain. We're going to have further meetups that show you the connections between two. This evening is about what is zero-knowledge proof, how does it work, and seeing a live example.
Thank you very much, John. Remind me to stick to the 4x4 Sudoku, not go into the 100x100. Thank you very much, everyone, for being here. So I'm going, as John said, I'm going to talk to you mostly about the theoretical aspects of zero-knowledge proofs. I'm going to concretely dive a bit deeper into the protocol that is mostly in use nowadays. It's called ZK SNARKs. Okay? For whoever wants to know, it stands for Zero Knowledge Succinct Non-Interactive Arguments of Knowledge. Yeah, a bit of a mouthful, but let's call it SNARKs for the purpose of this talk. So I'm going to start with explaining a bit more how to solve this Sudoku problem where one doesn't know if there is a solution, but with a physical example. Okay. So let's say that there is Peter here, who's going to become the prover soon, and Valeria, who's going to be the verifier. And Peter has the solution to a specific Sudoku that he wants to demonstrate or prove to Valeria that he indeed does have the solution. But he doesn't, of course, want to ruin it for Valeria and show her the solution. So Peter takes all the Sudoku cells. They're all filled in with a solution, and he basically turns around all the cards, let's call it. Each card is a cell, puts it on the floor, okay, in order. And then he simply turns around the cells that were public, right? Every Sudoku puzzle has some cells that you can see. And now simply he says, so in this process, he's basically committing to the solution, right? After he puts the cards down, he cannot change any number in his solution, right? So this is what we call a commitment. And after he unveils the public information, he tells Valeria, okay, now you tell me, pick if you want randomly, whether you want to verify the rows, the columns, or the boxes, right? Which are also called groups. So Valeria says, okay, randomly I chose the rows. Rows, please, right? Very polite, Valeria. So what Peter does is take all the rows, puts them into bags, okay, 9 different bags, and simply mix them, right? Now the numbers are there, but they're not in order, right? There's no way to know what the order was from before. And again, now Valeria takes all the bags and checks one by one to verify a very specific constraint, that is that the very well known that every row needs to have cannot have a repeated number, right? It has to have every number from 1 to 9. So so she tries all of them, but maybe she says, you know, you matched it so that the rows would pass the test, but maybe the columns still don't pass the test, right? This is a possibility. So we give the possibility to do this procedure several times. Now we can think of the computational version, right? John was saying before that we have a computation on some data that we want to prove without revealing the data, right? So let's use the Sudoku example as a way to understand this. We have some function that takes 2 inputs, x and y, right? In this case, the x is the private input, which is the hidden Sudoku cells that are part of the solution. And then you have y, which is the public ones. F is simply the program that checks that the solution is legal, right? Satisfies the puzzle. Now the statement of the proof is basically Peter knows some x such that f of x and y is satisfied, right? Is 1, right, in binary terms. So how does he prove this, right, to Valeria without revealing x, right? This is the whole point of zero-knowledge proofs in the computational sense. So what do we get from zero-knowledge proofs, really? Let's put this a bit into perspective, right? Zero-knowledge proofs offers us these 3 properties that are very essential to the specific constructions. In the situation of the snarks, we have completeness, right? Which means that if Peter knows the solution, he's always going to pass the test, right? The constraints are set in such a way that whenever he's challenged, if he indeed has a solution, he's always going to pass it, because that's what the constraints are for. then there is soundness, right? If Peter cheats, then Valeria will catch him with a probability bigger than a third, right? This is because she has a random choice of between rows, columns, and boxes, right? 1 out of 3. So if now we allow the procedure to be repeated, then Peter cannot cheat with only probability smaller than 1 over 3 to the n, which can get ridiculously small with the repeating of procedures. And finally, and probably one of the most important as well, is zero knowledge, right? This is the whole point of zero knowledge proofs, that at the end of the day, Valeria learns nothing about the solution except that it is a valid solution. Yes?
Given all the rows in the random order, don't you get information from it because you know the public dots on the 9 by 9 square? I mean, you can see what matches.
You don't know which, right? I mean, the relationship between the rows is given by the columns, right? So at the end of the day, if you only get the row, each bag has 1 row. But you don't even know because which row belongs to actually, which bag belongs to which row. So maybe you don't have that information specifically. Maybe for specific Sudokus, you can get it, right?
But won't they all have 1 through 9? All the bags?
No, but what he's asking is if you get you can pinpoint the public numbers back into the Sudoku, right? And then you could get some information. Anyway, let's continue. Maybe we can have this discussion offline. So what we've looked up to now is basically an interactive proof, right? We had Peter and Valeria interacting to get the solution. So in general, how it would work is Peter commits to some data, Valeria introduces some randomness, right, into the problem and challenges the prover with some query. In the case of the Sudoku, again, is rows, columns, or boxes. And of course, Peter needs to answer the challenge with some answer that satisfies the query, and Valeria can easily verify that the solution is legal, that the answer is legal. This should say non-interactive proofs, but so in the non-interactive example, we have instead a pre-processing of the challenge. Okay, so we process the challenge in an algorithm in a setup state that basically encodes the challenge and the constraints of the challenge into a proving and a verification key. Okay, now we're getting closer to ZK snarks. And then Peter, the prover, simply uses the proving key and his data to prove all of the constraints at the same time. Okay, so he doesn't only prove about the rows, he doesn't only prove about the columns and not about the boxes, all of them at the same time. And some more constraints that Kobe here will explain later.
So which site has the setup?
No, so the setup, okay. So I was just going to get to that. The setup actually requires, the setup now, instead of the verifier choosing the randomness or giving the randomness, it is now the setup person or entity, and I will discuss exactly this at my last slide actually, that takes in the randomness, okay? The randomness actually needs to be destroyed after, so there needs to be some kind of trusted computation, but there are some solutions I will mention later. And because if not, one can fake proofs if he has this random data, right? If you have the randomness, the cryptographic randomness. So, okay. So we've now talked about the solution, the Sudoku example. Let's think about more specifically what are we talking about when we talk about constraints, right? We want to think of it more in mathematical terms, right, in order to be able to use them. So let's put the example of this statement, for example. I know the factorization of a very large number. Okay, so there is a public large number. You can think about it in terms of prime factorization, but I want to leave the prime side out of it for now. And I have two numbers that multiply to this large number, right? But I do not want to give you those numbers. I only want to prove to you that I have the solution, right? So we can look at the left example, which is basically a single constraint, and this is the problem, right? X times y equals z, right? This is a single constraint. And from this, we can actually build many constraints, right? So what have we done here is we've taken constraints and translated them into circuits, right? Into arithmetic circuits, which I'm not going to talk about, I'm not going to explain the definition or go into the definition, but it's basically some structure like this, where the gates are multiplication and addition gates, right? And now we can actually construct many, a circuit with multiple constraints, right? You can see here that there's many constraints, but actually at the end of the day, it's only one constraint. Furthermore, in order to use ZK snarks, the researchers developed a further way to represent constraints, deriving them from arithmetic circuits that are called QAPs. It's quadratic arithmetic programs. And they're basically a set of 3 sets of polynomials, let's say. One which is basically, and these polynomials encode the structure of the circuit, okay, the constraints that are in the circuit. And so we have the set of A polynomials, which are basically the left inputs. So if you look at here, we can see that A of X of G is 1 because it is a left input to the G gate. The B polynomials are the right inputs, and C polynomials are the outputs. Okay, so we have a very simple computation here, which is A times B equals C at the end of the day, right? And we've seen and we can extend this to multiple constraints. Now, when we use these constraints, what we're looking at in ZK snarks is actually to hide the data and the fact that the data satisfies the constraints. So how do we do this? In a very general way, we use discrete logarithm. Okay, it's a cryptographic problem that is considered to be computationally hard, which is basically defined as such. If I give you some element G in a group or something, or a field, and then and I give you also G to the power of X, it is computationally hard to find X, right? If you do it over the real numbers, of course, you can take the logarithm, the natural logarithm or something, but over a discrete group, you cannot easily compute it. And here we can see how we can compute, for example, the additive constraint hiding in the exponent. Okay, this is what we call hiding the data over the exponent. So basically, we take G to the power of X, times G to the power of Y, which gives us G to the X plus Y, right? We can do the same with multiplicative constraints. Basically, we get Y multiplications of G to the X, right? And this is how we can compute this in the exponent. Okay. Before you get confused by this slide, I would like to apologize because if I had a whole hour, I would go deep into the details of how these constraints are encoded in the exponent and what are the different computations that go on. But unfortunately, I don't have that time, so I'm going to stick to try to give you a bird's eye view of the functionality and of how the different algorithms work, right? So basically, there is 3 algorithms that define ZK snarks, right? One is the setup algorithm, which simply stated takes some constraints of a given problem and computes a proving key and a verification key, which, as you see, the proving key has some is encoded. That's where the constraint structure is encoded, and the proving key is given to the prover, who takes his private input data and the constraint data, right? In here, for example, the input data is the Sudoku solution, right? The hidden cells, and the constraint data is the Sudoku puzzle, right? The public cells that were known before. And the prover simply computes the zero knowledge proof, right? Which encodes the instance itself, right? The data with the structure. And the verifier takes the verification key and the zero knowledge proof and computes a specific function to verify that the data satisfies the constraints given, right, by the problem. Now let's look just a little bit deeper into how these 3 algorithms work. So follow me. The setup algorithm takes as input some constraints, okay? But the constraints are in the form of a circuit. Okay, we said we looked at how the constraints could be encoded into a circuit by looking at the topology of the graph of the circuit itself. And the circuit itself can also be represented as polynomials, right, which are the QAPs. So what happens during the setup is that these polynomials are evaluated at a random point. Okay? This is where the randomness is encoded now, right? This is where we put the randomness that is needed. And this encoding of the polynomials, these polynomials are then hidden in the exponent, right? Because we don't want anybody to know where they were evaluated at. And if they get all the points, you can just extrapolate. Point being that from this encoding in the exponent, we generate the proving key and the verification key, right?
So are these one-time keys or can you use them?
No, you can use them as long as you refer to the same constraints. You can use them as many times as you want, right? The setup is a pre-processing step, but that is forever for that specific set of constraints, right? Since once anybody gets the proving key, right? The proving key and the verification key are public, right? And anybody can prove or verify as long as they have, the prover, as long as they have the correct data.
And why would you like to change the constraints? When would you like to change?
For different problem, for if some regulations change. But in general, think about it as you keep them, you use them the same.
Sudoku problems in the world or something?
Yeah, for example. Kobe will get more in detail on that. So what happens at the prover stage is that he inputs the data and the constraints. He himself encodes the data into the polynomial coefficients. Okay? He does this by taking all the data, executing the data or computing the data over the circuit, okay, and extracting all the intermediate values in the circuit, okay? And then he basically computes an inner product or a dot product between the polynomials that exist in the proving key that have an evaluation at a random point and the coefficient that were just extracted. So basically at the same time, he's encoding all the data in the exponent, right? Again, as we saw before. So now what needs to be checked, what is left to be checked by the verifier, is that the data that was encoded indeed follows the constraints, right? So once we get to the verifier now gets the verification key, which has the original constraints and the structure of the circuit encoded into this verification key, and the ZK proof, which has the data tied to the constraints, and through some function that is called bilinear pairing, okay, because it's bilinear on the inputs, allows you to verify over the exponent that some function in the exponents is satisfied, right? This is the f of xy is satisfied, right? So I know I've mentioned a lot of terms, probably many that are not familiar, but this is in general or a bird's eye view, right? So
Maybe if you look like so, is there another randomness beside the setup?
right, so there is some randomness here too that I did not mention,
The
but
prover side?
yeah, the prover side. He uses some randomness to further encode or hide the polynomials themselves.
Okay, but here if the randomness is not honest, so it's not, might only reveal is that data, right? I mean, it's not.
It's
cheap,
you're pointing very good points. You're pointing out very good
No,
points.
I'm asking.
I don't want to get into the details because it's probably not the level that I wanted to go into. But let's talk about it later. So let's just have a quick look over of on the complexity side because it's interesting to know what it is composed of and the application of the blockchain that John was mentioning before. So the setup is, as I said before, actually needs to be computed in a trusted environment for the randomness, right? If someone generates the setup, as you said, you can manipulate the randomness or you can keep them randomness and then generate, it's like a backdoor, right, to generating fake proofs. So we don't want that. There is really nice solutions that exist for this, such as how to generate between many parties and then some kind of multi-party computation and things like this. The prover is very slow, actually. It's computationally intensive. There is cryptographic computations, elliptic curves, some Fourier transforms that you need to compute. There is some optimizations that are done, of course, and we're working on some acceleration for the prover. And finally, the verifier is actually very fast, and the proof is very small. This is where the succinctness, right, in the name snark comes from, because the proof is small and is very good, as you can see here. Both the fact that it's three, right, the fact that it's not interactive, the fact that it's fast verification, and that the proof is small is really good for the blockchain, right? Because a single person creates a transaction on the proof, so we can compute that locally. But then when he posts the proof on the blockchain, you don't want the proofs to take up, you know, a large space, because at the end of the day, everybody keeps a copy of the blockchain, right? And on the other hand, again, many people can verify this proof and the transaction and the validity of the constraints. So it means that being fast is really good. So I'm actually going to now give it to Kobe for him to explain to you a bit more in depth about Sudoku example.
Okay, so thank you, John, for showing the motivation why we want to solve these crazy Sudoku problems. We've seen that it causes wars, there are psychopaths. We want to solve this. And thank you, Daniel, for presenting the theory that has the mechanism to solve these kind of problems. And I really want to show you some actual code that solves some zero-knowledge proofs. And for that, we are using, in this demo, a very cool library called libsnark. It's developed by the Skipper Lab. It's released under the MIT license. And one of the advisors of the company, Eran Tromer, is actually a big part of it. And libsnark by itself allows us to construct prover verifier systems like the ones that Daniel mentioned, and it supports multiple, but we are specifically interested in the ZK snarks that Daniel mentioned. But before we get to actual code, I want to go a bit more deeper on a specific Sudoku problem. Because in order to actually code it, we have to understand the arithmetic circuits that we want to code. So let's look at a smaller Sudoku problem, a 4-on-4, like, not go crazy. And let's understand what are the requirements from a correct or legal solution. So the first requirement is very obvious. Each cell in the Sudoku solution must be between 1 and 4. We can't have 5s, we can't have 10s. That's just not correct. The second constraint or second requirement is more important, is the actual Sudoku hard part. And that each row, each column, and each group must have each number only one time. That means that the row must have 1, 2, 3, or 4, and not 2 1s, 2 2s, or whatever. And if we are considering a situation where someone provides a puzzle and the prover provides the solution, then given a puzzle which has some blank spaces and given a solution which is filled with numbers, we want to make sure that the puzzle and the solution agree on these cells which are revealed. So the solution must have 3 on the top right cell as well. Okay, so let's try to solve or define the arithmetic circuit that will define the first constraint, that will make us realize that each cell has only 1, 2, 3, or 4. So to do that, first we want to convert the representation of the numbers to some other representation. This will also help us later in the second constraint, but let's look at this now. So let's say we have the number 3 in the top right cell. The representation we want to have for it is this flags array. The flags array will be attached to each cell. We will have a different flags array for each cell. And it will be of the size of the legal numbers, the possible numbers. So the flags array would be of size 4 because we have only 4 legal numbers. Okay, so in the case of 3, the flags array will look like this. We will have 1 turned on, like we will have the third bit turned on, and all the others will be zeros. That means that the flags array has 1 in the third position from the left and zeros in the other positions. Okay, we have this representation. Let's see how to use it. So now I'm actually going to define what is the arithmetic circuit. So it is actually defined by this formula on the top right. Cell value minus I times flag at position I equals 0. This is a constraint we will define for each of the possible i's. I would go from 1 to 4. But it's not very obvious why this solves the problem. It's kind of an obscure formula. So let's see why it works. So let's say we want to prove that this cell has the number 3. And this is the associated flags array. For I equals 1, we do the subtraction first. So we have 3 minus 1, we get 2. We multiply it by the flag in the corresponding position, and we get 0, like the constraint requires. Okay. For I equals 2, it's very similar. We do 3 minus 2, we get 1, multiply by 0, we still get 0. But this is the interesting part. For I equals 3, which is the actual number that is in the cell, we get this situation. We do 3 minus 3, we get 0, but the flags array has 1 in this position, but because the subtraction was 0, we still get 0. Okay, I equals 4 is the same as 1 and 2, let's move on. Okay, so this works, but why wouldn't it work for a number 5 with the same flags array? Let's see. So this same flags array with the number 5 will give us, for I equals 1, we still get 0. For I equals 2, we still get 0. But for I equals 3, we get 2 eventually. And what would happen here is that we would not be able to satisfy the constraints that we defined for ourselves. We would not get 0. And then we would not be able to generate a proof. The proving process would fail. Okay, let's move on. So now we are talking about the second constraint, which is in this case that each row, each column, and each group must have all the numbers and only ones. For this, we will use this new representation, and we will use it in some tricky way. So let's look at a concrete example. Let's look at the first column in this solution, and let's put it at the bottom. And we will stack the flag array representation for each of the numbers on top of each other. Now, we will do a sum. We will sum all of the columns, and we expect to get ones. This would be our constraint, that the sum of these columns is 1. This is, again, not very obvious straight away why this works. So let's see what happens when we have the same number in the column. So here we have 4, 1, 3, and 1. And when we will sum these flag array representations, we will get eventually this result, which has 2 and 0. And this doesn't work. So again, now because the constraints are not satisfied, the proving process would fail, and we would not get a proof. Okay. So this is nice. This allows us to actually, given a solution and a puzzle, to actually verify that it's a correct solution. So now let's talk about a bit of a more design issue or design thing. We want to have a proof function or a proof circuit that receives an input as puzzle and a solution. This would be, for example, in the terms that Daniel mentioned, this would be Peter. He would have the puzzle and the solution. He would feed them into a prover, and we will get a short, concise proof that he actually has a solution for this puzzle. And Valeria, on the other hand, will receive the proof that Peter created, and given the same puzzle and this proof, would be able to ask the verifier function, is this a correct proof or not? Does Peter actually have a solution or not? And she would get either true or false. Okay, so now I actually want you to see some code that shows how it's done using LibSnark. And for that, we prepared an interactive notebook using Jupyter or IPython for those of you who know it. And it is actually an environment that allows you to experiment and work with zero-knowledge proofs. And it serves a lot of the boilerplate that needed to be done. And we will create this environment and do all of the steps that we mentioned. So let me just go into that. Okay. I'll admit, it still looks like a presentation, but it's not. It's actually an interactive notebook. So the first thing we do is initialize libsnark. But that's really boring, and that's a lot of lines of code, and we will not see that. The second thing is we want to define the constraints that are related to the Sudoku problem. So first I have to introduce some new terms. In libsnark, when we want to define constraints and construct proofs, we work with two things. We work with gadgets, which are components, classes, that embody a set of constraints, and also how to satisfy them. And the other thing is that we have a protoboard, which is a component that contains the constraints related to the problem you're trying to solve, and the variables required to support it. So this means that you create some gadgets for the Sudoku problem. So in our example, we would have a Sudoku cell gadget, which will embody the constraints that are related to how a cell is legal, has the numbers 1, 2, 3, or 4. And the other thing is that we would have a Sudoku closure gadget, which will embody the constraints that mean that a row has the numbers 1, 2, 3, and 4, and not the same number twice, or a column or a group. It's very general. And once we construct these gadgets, we can combine them together in a parent gadget, which we will call a Sudoku gadget. And this will put all of the constraints together on the entire board. And we'll put that on the protoboard, and then we can construct the proof. So let's see how that happens. First, we create a protoboard, and then we start defining our gadgets. So as you can maybe imagine, the Sudoku closure gadget is big. It's not very concise writing these proofs or writing these constraints. The proofs themselves are concise. But let's see an example of the Sudoku cell gadget.
So how big?
How big is the code?
No, the output.
The output is not yet, and I will show you actual statistics later. Okay, so the Sudoku cell gadget is again about this individual cell containing the numbers 1, 2, 3, or 4. So the important part, let's see if this works. It doesn't. The important part is this line, which is actually very similar to the formula I wrote at the top right before. We have cell value minus I, flags at the position I, and 0. So this looks a bit like an arithmetic circuit constraint, but we don't have multiplication or equality here. But what this means is that the left part, number minus I plus 1, multiplied by flags at position I, must be equal 0. This is what this line means. Okay. Now let's assume we already have the Sudoku cell gadget and we already have the Sudoku closure gadget, and both of them together create the Sudoku gadget. So let's create an instance of it, and this is for a 4-on-4 Sudoku. This is why we have 2 there. And this gadget is prepared to accept an input puzzle that has some blank spaces, some blank cells, and the solution for it, and from that generate a proof. So first of all, we need to go through the setup phase. We need to create a proving key, and we need to create a verification key. So this is kind of what it looked like. At the top, we see that we call a generator function with a specific constraint system, and we generate a key pair. The key pair size, or more correctly, the proving key size is around 700,000 bits. That's pretty large for this kind of small problem. The verification key is small. It's around 3,000 bits or 4,000 bits. And now we want to prepare a specific puzzle. So what I'm going to actually do, I'm not going to go into that, but what we see here is the same puzzle that we saw in the slides before, a 4-4 Sudoku, but we have some blank spaces. This is shown here by the rows that has zeros in all of them. And what we see here is actually an 8-bit representation of the numbers in the cells. Okay. So now let's say we're Peter. We have a specific puzzle, and we want to prove that we have a solution for it. So for that, we need to store the solution somehow in code. This is what we do here. This is very similar to the puzzle, but it doesn't have any zeros, doesn't have any blank spaces. So once we do that, we can check, did we satisfy the constraints? And Peter checked that on the protoboard, and he see that it's not satisfied because Peter made a mistake here. He actually put the number 5 at the bottom. So the constraints were not satisfied. So, okay, Peter tries again, tries not to do mistakes or cheat. I don't know what his motives are. So he puts the correct solution. And now he checks it again, and we see that it's actually now the constraints are satisfied. Okay. Once that is done, Peter can call the prover function together with his proving key, the input puzzle and the input solution, and get a proof. So this is something that happens inside the prover. This is all the steps that happen in the theory side. We will not get into that. But let's see some statistics on the proof size. So the proof size is constant. It's very small. We can see that it's around 2,000 bits. That is something really small, and it stays the same for any size of problem. Okay, now that we have the proof, Valeria can take the proof and the puzzle and verify that this is actually a solution, that there is actually a solution. So the way she does that is by calling a verifier function and checking if this is true or not. Okay. I think it's not working. I'll try anyway. Okay, so this worked for Valeria. She checked that the proof is actually correct, and that Peter actually has a solution. But if she tries to use the same proof for another puzzle, I change the numbers a bit, she will get that this proof does not correspond to a solution for this specific puzzle. So this is a way to actually create zero-knowledge proofs using Leaf's law. Okay, so let's go for a few more minutes into the slide. So let's talk about some conclusion to what we've seen and to what we can do. So we've seen how to create a non-interactive zero-knowledge proof from scratch for the Sudoku problem. So we actually know how to do that from scratch, and we actually code it now. But obviously, Sudoku problems are not that interesting in the real world. We don't actually have these wars that John mentioned. But this technology can be applied to many other business processes. So you are more than welcome to visit us and experiment with this environment or just learn more. We're just down the hall right there. And if you're a developer and you heard this and you found this interesting and you want to build products that use technologies like this and solve real-world problems in the context of blockchains, we are hiring. Just shoot us an email to jobs@QED-it.com, and we'd love to hear from you. Thank you.
I actually would like a quick poll. So the theory part was pretty intense. Raise your hand if you agree. Okay. The practical part was pretty intense. Raise your hand if you agree. Okay. But the practical part showed you how to actually create proofs. So what we're doing in this company is taking this very sophisticated technology and making it practical. The parts that we didn't describe, connecting it to the blockchain, making sure that those proofs solve the actual problem that you need to solve. This is the bread and butter of what QED-it is doing. And when you see the reaction of the people that are going to get this as a product, they understand that we're taking this moon technology and making it available for the entire blockchain community. There are others in the world that are looking at this technology very intensely, and we're part of this larger community of people that look at ZK snark and zero-knowledge proof in general as the solution to this problem of confidentiality. So thank you very, very much for having joined us, and we hope that to have more such events in the future. Thank you all.